Let's check. Hello. Check. Hello.
Yeah, you guys. No, sorry.
Hello. Check.
Can you hear me okay?
Hello.
No problems.
KT चाहिए. KT चाहिए. Hello. Hello, sir. Can you hear me now? Hello. Hello. Nishant. American expressions ಅದು ಅಲ್ಲ ತಲೆಗೆ ಅಲ್ಬೇಕು ಲೈವ್ ಡಾನ್ಸ್ ಬಂದಿದೆ ಅದು ಗೊತ್ತೇನು ఇంకోటి పెట్టారు అవును ఎట్లు పెట్టారు ఆ బ్లాక్ ఉన్న సిల్వర్ Sir, can you confirm once? Can you hear us now?
I can hear, but quite bleeding.
Perfect, sir.
Yeah. It's clear. It's good.
Sir, you were saying something? Hello? Yeah, yes, sir. You said something. Can you hear us? Okay, sir. Okay, sir. So now I'm giving we're shifting you onto the main stage set. So like the auditorium is 500 seating capacity, and we are also screening this lecture on YouTube and all to all the RGUKT campuses. Okay, sir. Yes, sir.
Very good morning, everybody. A very warm welcome and delightful day. Welcome you all to the day 5 of the Qiskit Fall Fest 2025, proudly being hosted by RGUKT Srikakulam and sponsored by IBM Quantum. And I hope you all are having a refreshing start to the day, carrying along the same spark that of curiosity and enthusiasm that has been lighting up the entire week. And from decoding qubits to diving deep into the hybrid algorithms, every single day has been a celebration of learning. And I'm so sure about that. And today we continue that journey with even more brilliance. We have witnessed incredible energy, thoughtful participation, and some truly inspiring sessions so far. And that momentum doesn't stop here. Day 5 is going to be the next level one and to be yet another powerful blend of insight, innovation, and inspiration. So let me walk you through what we have lined up for the entire day. We begin our morning with a virtual guest lecture by an extraordinary personality, Dr. Srikanth Thudumu, Director of Artificial Intelligence at IAAIR, United States. His work in advanced AI technologies across global domains has made remarkable impact, and we are honored to have him share his experience with us today. Following that, we will be having the continuation of our hands-on workshop on Qiskit, mentored by Dr. Gnan Yala, CTO at datatech.ai, a researcher known for his deep work in quantum machine learning and hybrid algorithms. His sessions have been a perfect fusion of concept and code, and today's continuation promises even more exploration and excitement, and I am sure of it. And that's not all, guys. We also have an in person workshop by Mr. Tilok Sadhu Khan, quantum computing engineer and quantum developer at CDAC Bangalore, who will be guiding us through the Qniverse platform, helping us translate theory into tangible interactive quantum experience. And post lunch, we'll be having a very special occasion, the inaugural ceremony of the hackathon. We are truly honored to have with us some special delegates to inaugurate that 48-hour long hackathon. A small and huge challenge at the same time that will test not only your technical skills but also your creativity, teamwork, and problem solving spirit. So, gear up, everybody. This is where ideas turn into innovation. And before we dive into the first session, let's take a moment to appreciate the incredible energy you all brought up to this fest so far. The questions, the curiosity, the hands on engagement, it's been phenomenal, really. As we step into today's session, let us continue to learn, collaborate, and challenge ourselves because that's exactly what makes Qiskit Fall Fest so special. And now for the start of the day, I'd like to invite the lead organizer of Qiskit Fall Fest 2025, Mr. Katam Nikhil Teja, to introduce our first special guest today.
Good morning, everyone. It is my distinct honor and privilege to introduce our guest lecturer for today's session, Dr. Srikanth Thudumu, Director of Artificial Intelligence at the Institute of Applied Artificial Intelligence and Robotics, United States. Dr. Srikanth leads IAAIR's strategic direction, research initiatives, and industry collaborations, driving innovation at the intersection of artificial intelligence and real world applications. His expertise lies in productionizing AI research, turning academic breakthroughs into scalable, high impact industry solutions. With a PhD in artificial intelligence, he has dedicated his career to operationalizing AI into practical domains, focusing on ML model reduction, AI driven automation, and cost efficient AI adoption for business worldwide. Before joining IAAIR, Dr. Srikanth served as a senior research fellow at the Applied Artificial Intelligence Institute, Deakin University, where he led groundbreaking projects in collaboration with CSIRO and the Australian Department of Defense. His work includes the creation of a digital twin for a brain controlled wheelchair, a context aware neural search engine, and an advanced image processing platform for merchandise. Innovations that have not only gained industry recognition but also made tangible real world impact. Beyond his technical excellence, Dr. Srikanth is deeply passionate about bridging the gap between research and application and continues to mentor aspiring AI scientists, engineers, and researchers across the globe. In fact, I've learned about applied research importance through his work and through their website. We are truly honored to have him with us today to share his insights and experiences at the forefront of applied innovation. Ladies and gentlemen, please join me in extending a very warm welcome to Dr. Srikanth Thudumu. Sir, the virtual dais is all yours.
Um, Thank you very much. Can you all hear me? Uh,
Yes, sir, we were able to hear you.
Can I share my screen or should I be just talking?
You can share your screen, sir.
So, thank you very much. Let me share my screen. All right. Can you all see my screen?
Yes, sir. Perfect.
Excellent. First of all, thank you so much for that wonderful welcome. So, good morning, everyone. So, it's amazing to see or hear such an energetic crowd here at Qiskit Fall Fest 2025. Even though I'm virtual, I can hear that energy through uh, Nickel and you know from his words. So my name is Srikanth, and I currently work as the director of EI, the Institute of Applied Artificial Intelligence and Robotics. And over the past several years, my work has focused on quantum machine learning, hybrid algorithms, applied AI, and building practical systems that bring cutting-edge research closer to real-world applications. So, what excites me the most about this event is that it's just about listening to talks. It's also about building. So it's about exploring new ideas together. So quantum computing and AI are no longer distant concepts. They are kind of rapidly becoming tools we can use today. So I have spent a big part of my career working on applied AI and also on more recently how quantum technologies can push the boundaries of what AI can do and how AI can make quantum systems smarter and more useful. So I think events like this bring together brilliant minds, students, developers, researchers, all in one space, ready to experiment, collaborate, and create. I think through this fest, you'll all have the chance to get hands-on, to test your ideas, and to be part of something genuinely exciting. So, as we begin this journey, I encourage you to be curious, ask questions. You can challenge the assumptions, and most importantly, have fun. So, once again, I'm Srikanth, and I'm truly honored to be here with all of you today virtually. Let's make this fall fest a memorable one. So let me start my webinar today. So I'll be talking about quantum artificial intelligence. So let me move my slide here. So as you can see, what exactly is QAI? So we call it as quantum artificial intelligence. But what exactly is uh, this quantum artificial intelligence? So um, we are at the juncture of quantum computing and artificial intelligence. So, what do I mean by that? So, let me give you an example. Let's say, okay. So, throughout history, every major shift in computing opened new possibilities. Like if you take mainframes, they made large calculations possible, and personal computers made computing accessible, cloud computing and AI made data-driven applications powerful. Now we are entering another shift. We call it as quantum artificial intelligence. So QAI means combining the learning and reasoning abilities of AI with the special properties of quantum computing. So instead of just making current AI faster, QI, QAI can tackle problems that classical systems simply can't handle well, like large-scale optimization, complex simulations, or analyzing extremely high-dimensional data. So this future will not be purely quantum, it will be hybrid, meaning both classical and quantum computers will work together. And as computer science engineers, will be the ones building the layers that make this possible. So classical computers use bits, as you might already know this stuff, so which can only be 0 and 1. Quantum computers use qubits. I'm pretty much sure you all know what it is about. Qubits, which can be both 0 and 1 at the same time, we call that as superposition. Think of it like a spinning coin while it's spinning. It's not just heads or tails. It's in both states. Only when it lands does it become one or the other. Qubits can also be entangled, which means the states are linked. Changing one affects the other instantly, even if they are far apart. You know, millions apart. So when we combine these quantum effects with AI, we get algorithms that can explore many possibilities at once. So what do I mean by that? For example, let's take a classical search algorithm looks through options one by one. So a QAI algorithm can look at thousands of options at the same time and collapse down to the best one much faster. And this creates opportunities for breakthroughs in optimization, simulation, and learning paths. So why QAI matters? Today's AI is powerful, definitely, but also it's very heavy. If you were to train a large language model, it can take weeks on thousands of GPUs, and it can consume huge amounts of energy and electricity and cost millions of dollars. And even with that power, some problems are just too big. Let's take the traveling salesman problem. So if we have hundreds of cities, finding the shortest route requires testing astronomical number of combinations. A quantum system can actually encode all these probabilities at once. Let's like using qubits, making it far easier to find a good solution quickly. So let's also take another example of drug discovery. So classical computers take months to simulate like how molecules interact because the molecular behavior itself is quantum, as everyone knows. Whereas a QAI system can model all these behaviors much more naturally. And this saves both time and the cost. And this is why QAI matters. It's not just an upgrade, it's a way to solve a different class of problems entirely. So, what exactly are the key building blocks of QAI? Like, think of QAI, quantum artificial intelligence, as a technology stack. And there is a good reason behind why I'm giving this analogy. So at the bottom is hardware, which is the physical quantum computer you might have seen in pictures like IBM's superconducting systems, or if you take IonQ's trap ion machines. And on top of that, there are quantum algorithms. So you might have heard of Grover's algorithm for search or QAOA for optimization and all that stuff. So these are like the sorting or graph algorithms we use in traditional computing, but designed for quantum machines. Right? Then come quantum machine learning models built using quantum circuits such as quantum neural networks. We call it as QNNs. To make these quantum pieces work with classical computers, we use a middleware, which is kind of a software that lets the two communicate between each other. And finally, developers the right code using high-level frameworks like Qiskit or TensorFlow Quantum or something like that. For CS engineers or computer science engineers, understanding this stack is very similar to how we think of hardware operating systems, OS, and software layers in traditional computing. So from QML to QAI. So right now we are right now quantum machine learning is about improving basic ML tasks like classifying data or finding patterns. But QAI basically goes further. A lot of people does argue that QML and QAI are the same, but they are not. So QML is about improving basic ML tasks, as I mentioned earlier, classifying data or finding patterns. But QAI is different. It goes further than that. It's about making AI systems more intelligent, not just more efficient. Let's take an example of reinforcement learning. So, teaching a system to make decisions by trial and error, a classical RL agent, reinforcement learning agent, explores one strategy at a time, whereas a quantum RL agent can explore many strategies at once. So, think of the possibilities because the policies are encoded in a superposition of states. So let me give you an example. Let's say if you are training a robot, right, to navigate a warehouse, and a classical computer may take thousands of attempts. Let's take a QA system for the same scenario. This particular QA system can evaluate many navigation paths simultaneously, and it can converge to an optimal path faster. Another example I could take is a team of autonomous drones coordinating flights. Right? A QAI multi-agent system can optimize coordination in real time, something classical systems struggle with at scale. So, what exactly is the recent progress in quantum algorithms? So, I mean, the field we're talking about QAI isn't just theoretical. There's a measurable progress out there. So there's something called as variational quantum circuits. They are trainable circuits that very much behave like a neural network layers. And there is something called as quantum kernels, which give classical algorithms access to richer representations of data, making classification and clustering even more powerful. And there is also something called as Hilbert space. Basically, it's like a mathematical space where quantum states live in there. Like unlike ordinary 2D or 3D space, Hilbert space can have exponentially many dimensions. And this is what allows quantum algorithms to represent complex patterns more compactly than classical models. Again, let's take an example. So researchers have already used quantum circuits to classify sentences in a language task. Even with limited hardware, they achieve performance close to classical models, but with less computation. And another team used quantum methods to estimate molecular energy levels more accurately than classical simulations. And we got frameworks such as Penny Lane, which let developers combine both quantum and classical ML in the same workflow today. If you're interested in understanding more of this research, so we recently published a paper and we'll be presenting at the 2025 IEEE conference on quantum artificial intelligence the first week of November in Italy, Naples. So if you're interested, it's available in archive. Just Google my name and you can find my recent papers and just go and read it. You'll find it very interesting. So the hardware evolution. So let's talk about hardware evolution. So the quantum hardware today is now very much similar to the early personal computers. Let's go back. Let's rewind back to 1970s. It was, but it is very limited. The main issues are noise, like what you call unwanted interference or decoherence. Like when I say noise, it's unwanted interference. Like you literally have that interference which you don't want it to have, and then there is something called as decoherence, which is basically loss of quantum information over the time. And then error mitigation is like noise cancellation in audio. It doesn't remove all noise, but it makes the signals more cleaner. This allows slightly larger models to run reliably. So in the next few years, companies plan to scale their machines to over 1,000 qubits. You might have heard of it or you might have read a research paper. So eventually they will achieve fault tolerance, which means the system can run long, complex problems without actually breaking down. So for quantum artificial intelligence, this is kind of a big deal. So more qubits and more stability means more complex learning tasks, like take the problems of large optimization problems of real-time control systems becoming practical. So what happens in the near term, right? In the next 4 to 0, in the next 5 years. In the next 5 years, again, if you want more information on that, I would strongly encourage you to go and read the paper we recently published. We recently published an archives in a preprint, but it's been selected for a conference, as I mentioned earlier. So again, in the next 5 years, we'll see QAI used for targeted high-value problems. For example, airlines and shipping companies must constantly update their routes and schedules. So classical traditional computers, they can take hours to optimize all these processes, especially during disruptions. Whereas the QAI system can evaluate many route options at once and find near optimal solutions faster. And another example I could take is cybersecurity, right? Quantum anomaly detection. By the way, anomaly detection is what I did in my PhD. So let's take quantum anomaly detection. It can analyze massive logs and network flows to detect suspicious activity earlier. And during my PhD, I realized, so I've worked on my PhD research area is anomaly detection in high-dimensional big data. And when there are high dimensions, there's a problem called the curse of dimensionality. And detecting anomalies in that particular big data is a humongous, it requires humongous computational power. And we can't even micro manage or micro detect all these anomalies. You can only identify the spaces where there are potential anomalies. If we want to apply this quantum computing in that anomaly detection space, think of how many fraudulent transactions we can pinpoint. Think of how many fraudulent or intrusions in the network we can detect, right? And in drug discovery, there's a problem called drug discovery, right? So you require a lot of computational power. Let's say there is a new disease that comes up, and there are there's a new virus that comes up, right? And there's a lots of research, and there's a lots of research papers, and there's lots of research that's been happening, and there's lots of data in the Excel sheets or spreadsheets, and there's a lots of data in the brain of the scientists. So currently we are just limited. We cannot, see the relationships between all these data sets. They are not fused because we do not have that computational part. And given a virus, understand its DNA and all that stuff, and see what is the best combination to start a research, to start research and coming up with a drug that could actually kill that virus. So now we have to do a lot of things. The data is scattered across various sources. The data is scattered across various places, and there is no relationship. Think of having that quantum computing, and then where it can identify its relationships automatically given the viral structure or whatsoever it is, and then going to these resources, identifying the combinations and relationships, automatically establish the relationships, and then identifying the drug. If we were to have a situation like COVID or coronavirus or something like that, it can potentially come up with a solution even more faster than the usual one, right? Physically, and we can test it physically, and we can reduce the number of compounds that need to be tested, and we can save millions of people or millions of dollars. Let me put it that way. Of course, we need to do all this testing, on clinical trials and all that stuff. So, but potentially it can bypass that, the process of drug discovery, and start giving us at least something to test with, and it will make things faster. There is something called as a site feasibility analysis in pharmaceutical industry, where if someone were to come up with a drug a discovery or something like that, they need to you know uh, capture and gather all the data and try to see, the issues that comes with all these site feasibilities and whether the site is useful or not. So all these things can be easily solved. So, and there are something called as recommendation systems, like if you were to use Netflix or Amazon, I believe a lot of people use it. So let's say if you watch a movie or if you buy a product in Amazon, so you got the personalized products, but how many times you realize that it is not your uh, your what you wanted to have, right? And there is also something called as preference falsification. Sometimes in the public you might say, "Hey, I like this one," but in reality you might not because of various section of this. When you hyper personalize all these events, is there an AI that could detect without actually spending a lot of time? So quantum computing can actually solve this problem. So you can get products even the moment you think you will get the recommendation, something like that. So quantum computing is that. So that's near-term applications, and mid-term applications. So once the quantum hardware gets more stable, applications will definitely expand. Let's imagine a scenario called autonomous vehicles, that not only drive themselves but coordinate citywide traffic, right? So let's say here in the states we got autonomous vehicles, they are taxis. So let's say if a autonomous vehicle is going right in one direction and there is a traffic event or something like that, how can it understands there is a traffic problem real time, and how can it be how can it take a take another route or something like that, right? So there's a lots of traffic related issues. So a QAI, let's say if you have a controller that's based on QAI, it can consider thousands of traffic states at once, adjusting its signals and routes, and then it can avoid congestion. And then another example that I could do is a global supply chain, which can be optimized dynamically, responding to factory shutdowns or natural disasters in real time. And in cybersecurity, we have ever heard of quantum cryptography. It will provide data, and quantum cryptanalysis will expose weaknesses in classical systems. And let's take robotics. QI can simulate various robot configurations just like that, and and control policies faster than classical simulators. You can speed up innovation in manufacturing, and that's midterm. So then long-term vision, which is beyond 2035. And again, if you need more information, I always refer to my paper because it's been we gave a good amount of thinking, and then we reported with our uh, lit review. So please go and have a look at that paper if you have more questions. So beyond 2035, we'll see QI not just as specialized tool, but as a core infrastructure. So imagine an intelligent global power grid, right? QA agents monitor energy demand and supply worldwide and adjust flows instantly to prevent any blackouts. Financial systems could use this QAI to detect systematic risks before they even cause crashes. And large transportation networks could self-optimize without the human intervention, without human planners. And at this stage, QAI won't be a separate quantum box. It will be integrated with classical computing systems and human decision-making tools, creating a powerful hybrid intelligence. So, what's the role of QAI in science and engineering? And science and engineering will see some of the biggest gains for sure. As I mentioned earlier, drug discovery currently takes 10 to 15 years. Each drug discovery currently takes 10 to 15 years. That was I was talking about, and millions of dollars. QAI can actually simulate that molecular interactions in quantum terms, dramatically speeding up early phases of development. And if you were to take material science, which is going to use QAI to find new compounds for clean energy companies, technologies, for example, solar panels or more efficient batteries. If you were to take climate modeling, quantum algorithms can process humongous amounts of data to simulate Earth's atmosphere very precisely. So engineers solving partial differential equations, like you know partial what are partial differential equations? We call it PDEs. They do it for heat transfers and for structures and fluids, right? We can actually use this QAI to speed up those simulations. Even in the aerospace, like mission planners, we can use this quantum optimization to minimize the fuel use and risk. So the other thing is QI in enterprise. So I mean, QAI is not just for for research labs. It will definitely going to reshape industries. Financial institutions can use quantum enhanced algorithms. As I mentioned earlier, we can detect fraudulent transactions much earlier than current systems. And because supply chains like those used by major e-commerce companies, it can react to they can react to supply chains can react to dynamically to disruptions. And as mentioned earlier, hyper personalization recommendation systems can become more personalized without consuming any more computing resources. So QAI can analyze large graphs of customers, products, and behavioral patterns very much faster. And in cybersecurity, again, QI can monitor the network behavior in real time. Blockchain systems can use quantum methods to make verification more efficient, supporting faster and more secure transactions. However, there are some technical challenges for sure. QI has got major obstacles to overcome. So, as mentioned earlier, noise and decoherence make quantum computers unreliable, right? If you were to take for long calculations, they are not reliable. So encoding classical data into quantum states can be very time consuming and sometimes removes the performance gain. We also don't have standardized benchmarks. For example, if you were to take ImageNet for QI, which makes it really hard to measure real progress. And obviously, there is a skills gap too. Not many engineers are trained both in machine learning and quantum computing. I believe this is going to be the future. If we were to work on this space at the juncture of quantum and machine learning, the jobs will be here at this juncture. So if you know a bit of quantum computing, if you know a bit of machine learning, and you start exploring and you become professional, and that's where the future is going to be, and that's where the jobs will be, in my opinion. And hybrid architectures are also technically challenging. Quantum processors work very differently from CPUs or GPUs, which means you need to have orchestration, which must be carefully designed. So, having said all of these things, there are definitely some ethical and societal implications for sure. QAI is powerful, but that power comes with responsibility. If only a few companies or countries control advanced QAI, they may have significant economic or political advantages, right? Let's say quantum cryptography and cryptanalysis will change how security works and possibly breaking current encryption standards, right? And if like QA systems could also behave like black boxes. I mean, you know what is a black box, right? Making it hard to understand how decisions are made. You know it works, but you don't know why it works and who it works, which is very dangerous in fields like healthcare. If you take healthcare, let's say you know if it is working, but if you don't know why it is working, then it's dangerous. And even if you were to take the law, take all the raw files, code files, existing files ever existed and come up with your own analysis, right? And you don't know why it is working. Defense, something is not working. You would have no clue why it is not, right? So that's dangerous. And that's why ethical standards, there'll be auditing systems and transparent algorithms need to be part of QI development from the beginning, not just after deployment. And then research and policy priorities. What do I mean by that? So for QAI in a sustainable way, research and policy must work together. So let's say we got a fault tolerant quantum hardware, which is essential for stable systems. So open benchmarks will make research reproducible and transparent. Universities and industry need to train a new generation of engineers who can think in both classical and quantum terms. And that's exactly why I'm doing this webinar today. So we need to understand both the realms. It's not just purely classical machine learning or traditional machine learning or traditional computing, it's also quantum. So when you combine together, because in order to be fully realize that quantum computing, it is going to take some time. So we'll be slowly going there. We cannot just go to the top of quantum computing. You have to take the steps, right? You have the staircase and you have to go through the steps. And I believe that QAI is the staircase. And very initially you have got classical computing, and the more steps you do it, right, will go to the top of quantum computing. So and very importantly, ethics and security must be built it from the start. And this is a lesson learned from AI. We need to apply it early for QAI. So, and yeah, that's the projected roadmap for supervised quantum machine learning, and that's coming from my paper. And again, I cannot really go through each and everything, but I kind of explain all these things in a way that you guys understand. But if you want to have more of this understanding, please go ahead and look at my paper, and you will have a lot of more intuition. But if you have more questions, you can find my email ID on top of the paper, and you can always send an email. So sometimes quantum AI is not just an academic area, right? Academic idea. It's a real technological wave. It's building slowly but steadily. As I mentioned earlier, in the early years, QAI will focus on specialized problems like optimization, simulation, and anomaly detection. But over the time, it will become a core computing capability, just like cloud computing is today. For computer science and engineering students, I think this is a rare opportunity. The people who understand QAI early will shape its future. And I'm very glad that you guys are already been doing so. Whether you work on infrastructure, algorithms, or applications, any part of QAI, your role will be very, very crucial if you understand both of these topics. So this isn't just about building powerful tools, it is also about building them responsibly. So QAI benefits society as a whole. So I strongly suggest, like, if you know quantum computing, that's perfect, that's very good. And if you also know machine learning, try to be at the juncture of both of them. So, and yeah, I understand that there might not be, a platform for you all to actually play with, computing, quantum computing. It is super expensive. I understand that. There are simulators like Penny. Just play with some. So one of my interns from Stanford University, we are trying to build a domain-specific language uh, for actually building, talking to Penny Lane and talking to quantum computing instead of doing all these, wires and entanglement superpositions, understanding all that terminology, technical terminology, which are really low level. What we're trying to do is we're trying to build. So we got another intern from the University UK, and these guys are doing amazing job. So if you are more interested, just go and visit our website and see our research and see the intern proposals that we're doing. You're more than welcome to get in touch. That's pretty much it from my side. I hope that helps. Are there any questions? I'm happy to take any questions. Can you all hear me?
Thank you so much for such an absolutely fascinating session, sir. All dear participants, let's show how much we loved this session with a big round of applause to us, sir. Thank you so much for your valuable time and insight, sir. You have walked us through the world where quantum meets artificial intelligence and the space that rapidly shaping the future of technology itself. From the motivation behind quantum AI to its building blocks, the beautifully connected how quantum computing hardware, algorithms, and AI models can together redefine problem solving from just pattern recognition to true cognitive problems and intelligence. He shared his insights into the progress in NASQ systems, the evolving roadmap towards thousands of qubits, and how QAI is already finding its way into science, engineering, and also enterprise. In areas like molecular modeling, material science, logistic optimization, and even financial forecasting. And of course, Sir didn't shy away from addressing the technical and ethical challenges from noise and talent scarcity to the critical need for governance, transparency, and responsible AI innovation. Sir, thank you so much for such a thought provoking and visionary session. Your clarity, patience, and ability to simplify such a complex frontier truly inspired all of us. On behalf of everyone here at RGUKT Srikakulam and the entire Qiskit Fall Fest organizing team, we extend our heartfelt gratitude for your time, your insights, and your valuable patience, and also your encouragement towards the next generation of innovators. Let's give a huge round of applause for Dr. Srikanth Durmuso for setting such a powerful tone for day 5.
Thank you very much.